Okay. It's problem 3. Okay. So problem 3, you see the figure in the bottom. Solid shaft or bar AB and another bar BC. They are joined together at point B, and they might be joined by welding. So there is no slipping between at point B. That means they work like a single shaft. So AB has a diameter 45 millimeter, and BC is hollow shaft. Internal diameter 30 millimeter and external diameter 60 millimeter. And length of this shaft, BC is 2 meter and AB is 1.2 meter. And what they like to say, that they apply torque clockwise at point B. Now they are saying what will be the stress at shaft BC and at shaft AB, and what will be the angular deformation, that they like to know. Okay, so let's see. They say reason shaft AB, shaft BC of a stepped shaft. Step means different diameter shaft. One is made of aluminum, other one is steel. That means AB is aluminum, BC is steel. Region AB 45 millimeter in diameter. Region BC 60 millimeter in. Could you hold on 1 second, please? Okay, sorry. So are you able to listen me?
Yes, sir.
Yes, sir.
Okay, so we are working on this problem. So you see the end of the shaft, it rigidly clamped. It rigidly clamped mean point NC and A. It cannot rotate. Okay, they are rigidly clamped. So rigidly clamped mean. Again, I like to show you what does it mean by clamp. You see there is a pin, right? So if I
Yes,
hold it tightly, if I try to rotate the other end, then this right now is slipping because my hand is slippery. Okay, but it is holding rigidly. So even if you apply torque, this end will not rotate. So they like to know what will be reaction torque at this end. Okay, and what will be the shear stress in the shaft. So it's saying find maximum shear stress. Right over here. Maximum shear stress and angle of twist on each portion of the shaft. If 4000 Newton meter clockwise torque is applied at point B, and G value of G for steel and aluminum is already given. Now, so what they like to know? Number one thing they like to know what will be the tau in both shafts, shear stress, and what will be angular deformation. That means theta equal to what? These two things they'd like to know. So theta, or if you say formula of tau formula, TOU, tau equal to T star C divided by J. This is tau. Okay? And theta equal to T star L divided by G J. G J should be at the bottom. Okay. So G J T L by G J. So this is our theta and tau. So you need to TC, or you can say TR, same thing. You see TR, that means radius of the shaft. If you know radius of the shaft, you can figure out the J. J equal to pi by 32 R to the power 4. So right over here, shaft diameter for both shaft is given. So R and J value we can easily figure out. Now value of the G is given. 28 for aluminum and 84 for steel. Then length of the shaft is L. So length of the shaft AB is 1.2 meter and BC is 2 meter. But we don't know what is the torque on BC and what is the torque on AB. So mainly we need to first figure out how much will be torque in AB and torque in BC. That we need to figure out. Then we can solve it. Now, this torque problem, this one, especially this one, is work almost same like a beam. In the beam, what happened? Say you have a beam and you have load at the center, or right over here. So what will be reaction? Reaction will be at 2n, and that reaction will be opposite of applied force. So you see external load, that means load apply from outside. So this one is say 500 Newton. Excuse me. This load you can see from outside, but this reaction force you cannot see from inside outside. Excuse me. I got cold, let me turn off the fan. Okay. So what I like to say, the always external load, you can see it from outside, but reaction and the internal load you cannot see from outside. So for this case, you see our external load is 40,000 Newton meter, and obviously this is torque. So how we can figure out the reaction torque? So we can think the torque, this is the shaft. At the midpoint, we have clockwise torque 4,000. So at the two end, that means point C and at point A. This is clockwise. So there will be a at point C and at point A. So at point C, I can say this torque is C. Hello. And at point A, torque is TA. And this one is 4,000 Newton meter. So we need to figure out this TA and TC. At the middle, they apply force load, that means torsional load, 4,000 Newton meter. It don't mean that AB is carrying 4,000 or BC is carrying 4,000. Actually, it would be shared by both shaft. So we need to figure out the reaction torque TA and reaction torque TC. Then you can solve it. Now, how we can figure out the TA and TC? Right, in beam problem, in the left side, you see we can figure out the reaction, this reaction. How? And if you take moment at this point, you will get this reaction force. Again, you take sum of Fy, you will get this force. But in torque, you cannot take moment. If you take moment, still this should not be zero. Still you have two unknown. Okay. So now we see we have two unknown and we need to figure out two value. So if there is a two unknown, then at least you need two equation. So how we can figure out this two equation? Other thing, the angular deformation at point B. B is the common point. Attached to it BC, also attached to it AB. So at point B, angular deformation for both shaft is same. I can say theta AB. That means at B point, angular deformation will be equal to the theta BC. That means angular deformation at point B. If I say these two is same, then we can, this is one equation, we can solve it this equation. And we need one more equation, because what is the theta? Theta equal to T into L divided by G into J. So theta B will be how much? TA LAB divided by G divided by JAB. Similarly, theta BC will be how much? Theta BC will be TBC. That means torque in shaft BC, or you can say torque C into L of BC, then you divide it by G and divided by J. Okay. Now, how we can figure out the torque in AB and BC? We have to make a free body. Without making free body, we cannot figure out the torque BC. So how we can figure out make the free body? For example, if we take the shaft AB, I'm separating AB from BC. So this will be my point A, and this will be my point B. How much torque in at point A? I assume the reaction torque is anti-clockwise torque working at point A is TA. That we assume right over here. So how much will be torque then at point B? So it's supposed to be equal and opposite of torque A. So at B, at point A, torque is anti-clockwise, right? So at
Yes,
point
sir.
B, torque
It will be clockwise.
and it will be TA. Okay. Now, if I erase all those things, then I like to show you something. Erase that one. Actually, we didn't apply any load at the middle like TA, right? We didn't apply. But now this TA, right over here, we have only TB at point B. This is the B is a common point, this point. So there is no TA, right? So this TA, we need to take it out. So how we can take it out? We can draw the BC, line BC, if we draw line BC. So line BC, this is my B end, and B, this is NC. And at C, we already assume anti-clockwise torque TC. Right? Now we see
Yes, sir.
at point B also have 4,000. This is already balanced. Right now we cannot apply 4,000 at shaft AB. So this 4,000 still I have to apply at point B. So at point B is coming 4,000 Newton meter. Now you see, if you join together point B, this TA will work like a outside member because TA actually is not there over here, no TA. So we need to take it out this TA. So this TA rotating clockwise. So right over here, I can apply a TA anti-clockwise at point B. So if you join these 2 points, B, just this end, you just match with this end, then what will be happen? This TA and this TA will be cancel out because this is clockwise and this one anti-clockwise. So at point B, you only have 4,000. That means you are getting this one. So what are we getting? So at shaft AB, amount of torque is TA. And at point B, if I represent point B with single torque, line, say line A, BC, this is line BC. So at point C, we have anti-clockwise torque TC. And this is my point B. At point B, instead of 2 arrow, I can represent a single arrow. I can say both are clockwise, but torque is 4,000 minus TA. I can say?
Yes, sir.
I can say, right? So now you see TC equal to 4,000 minus TA. We both has to be same. So I am getting torque at BC and also I'm getting torque at AB. AB torque is TA. Now those value you put it over here, then we can solve TA and TB. So if TA and TC, if we got T and TC, then we can easily figure out the shear stress. So let's see how we can solve it in the MathCAD. That will be easier for you. You can see the slide. MathCAD
Yes,
file.
sir.
Okay.
Yes, sir.
So same problem, I put it over here. And I just make it simple with one line diagram. I'm saying this is shaft AB. And this is shaft BC, this is joined at point B. Now at point B, we have TB. TB will be how much? 4,000. And we don't know how much at point C and at point A. So this is rotating anti-clockwise, so I put both on clockwise. But if you want, you can choose TA clockwise, anti-clockwise, and TC also clockwise, you can do it. Okay, then value will come negative. So this one, we know that this 4,000 torque at point B will be shared by AB and BC. So there has to be opposite of applied load. So that's I put both on is anti-clockwise. Okay, now at first, before you solve the problem, you have to figure out that what data is given. Right? You have to write down given all the value over here. So you see length AB equal to 1.2 meter, BC 2 meter, TB 4,000 meter already given right over here, TB. And GA for shaft AB is given 28 gigapascal, you convert in Pascal. Similarly, shaft BC, you convert in Pascal. This is the Pascal, okay, from gigapascal to Pascal. Then diameter of shaft AB already given 45 millimeter, shaft AB right over here. So you say DAB 45, then I convert in meter. DBCO, that means outer diameter of BC. You can use any subscript, you can use 1 and 2, still it is okay. So outer diameter of the shaft BC equal to 0.06 meter. This is internal diameter. Now, what they like to know, that shear stress at AB how much, shear stress at BC how much, and value of theta, that means angular deformation. And for these two value is related to these two formula. One formula for theta, other formula for tau. So we have to make free body that I showed you a while ago. That this is my original problem, first line. Okay, that we divide this shaft into two shafts. We took shaft AB and shaft BC. Then we try to balance this from the left side. So left side, we already think that reaction is anticlockwise, is TA. So TA anticlockwise. So obviously reaction at the TB has to be opposite and equal. So this is also TA, and you see a clockwise direction. Now at point C is this much, is anticlockwise, right? At point B, this 4,000 already I keep it same as at point B. Now this TA actually is not over here. So I need to remove this TA. So this TA I am putting clockwise. So I am putting a anticlockwise torque right over here. Now, if you just push together by hand from 2 point B together, then what will happen? This TA and this TA will be cancelled out because both are equal and opposite sign. So you have only 4,000, and we already have 4,000 over here. Then in the free body diagram, right over here, 4,000, this TA, just TA and 4,000 just represent with the single torque. Then we can say, because clockwise, this TB is positive, so respect to TB, TA is negative. So 4,000 minus TA is right over here. So now at point A and B, torque has to be same. Similarly, at point B and C, torque has to be same. So we can say TC equal to 4,000 minus TA. And because point B is the common point for both shaft, if point B on shaft AB, say point B shaft AB is rotated by 5 degrees, then BC also rotated by 5 degrees. So this is says center of the shaft. So before you apply torque, say B point is right over here. After torque, it came in over here. So angular deformation is theta is this much. So this point B, it remain in AB, also remain in BC. That is common point. So at that stage, we can say that angular deformation for both ends is same. That means we can say theta AB equal to theta BC. So what is the theta formula? We have only one formula, theta equal to this much, and J equal to this much. So this one is value of the J for AB. This is value of the J for BC. Over here is minus because it's hollow shaft. Then we apply this formula that theta in both shaft is same. So this one is theta for shaft AB. This one theta B for shaft BC, but both are same. So I say this value is right equal to this value. So TA, LAB 1.2, ZAB 28 gigapascal, 28 into 10 to the power 9. Value of J, radius is given 45 diameter. So value of J is over here. Now TC equal to 4,000 minus TA. So we put TC over here. Then length of the shaft LBC is 2 meters. LBC right over here is 2 meters. So if LBC is 2 meters, then you see all the data. We already got it right over here. Now from here, you can figure out TA by solving these equations, by simplifying. You got TA, you can easily figure out value of TC, because TC equal to 4,000 minus TA. So you got this one. This is TA, this is TC. When you see their summation obviously has to be 4,000. Now you figure out the theta for both shaft. Shaft AB, TA by LAB, J by GAB. So TA is this much, LAB 1.2 meter. You put JB, after solve, you got theta equal to 0.067 radius. Similarly, and if you convert in degree, it comes about 4 degree, 3.8 degree. Similarly, theta BC, we can figure out, and JBC equal to this much, theta BC is coming same. Because both are common point. If it's not coming same, that means we are wrong. Because right over here, we are thinking they both, because common B point is the common point, so angular deformation in the both shaft for B point has to be equal. So that's why, and we are getting equal. Okay. Now you figure out the shear stress. Shear stress is one formula, TR by J. So first figure out outer and what tau will be maximum at the maximum value of R. That means at outer radius for the hollow shaft. So for BC, if this is hollow shaft, right over here at the outer point, your shear stress will be maximum. So we need to use this formula. This is value of the J. So they figure out outer shaft radius of shaft BC. Similarly, now they figure out the tau BC. Tau BC, that means they took torque TA. Okay. So tau BC, let's see. That means at point AB. At shaft AB, we can figure out the tau AB. So tau AB equal to tau A into RAB. So after solve tau A, we get this one, 3.53 10 to the 7 Pascal. Then you figure out the tau BC. So we have won this formula. For BC, this will be TC. Okay. So for BC, this will be TC, not TA. So it will be this much. Okay. So you see, from here you can get the value of tau AB and value of tau BC. So any question from here?
Sir.
Yes.
So can you repeat that part where we change the direction of TA from anti-clockwise to clockwise in the diagram?
Your ID?
So 128.
128. One second, let me clear this figure.
Yes, sir. In here we change
The bottom line
clockwise to anti-clockwise. TA.
TA. You know,
yes,
TA,
sir.
TA in the middle line is anti-clockwise, right?
Yes, sir.
Anti-clockwise. But what is TA right over here? Clockwise, right? When you show you the arrow sign. So is TA, is say TA, this is my TA, positive TA. So I can say negative TA will be, this is anti-clockwise, so this is minus TA. And both are same, yes or no?
Yes, sir.
Both same. That we did over here. What we did at the point B? At point B, this is point C, this is point B. So over here TA, anti-clockwise, right? So this TA, instead of anti-clockwise, I like to put clockwise. Then this will be no more TA. but this will be negative TA, right? Negative TA.
Yes, sir.
Then we have clockwise, again 4,000. Now, if you add both together, then what you getting? 4,000 minus TA. Okay,
Yes, sir.
got it? That's okay. Now, in other sections, somebody asked me a question that this 4,000, we put it belong to shaft BC, right? So is it possible to put 4,000 with shaft AB? Is not possible, is possible, because I start from the left side. So in the left side reaction is TA. So B has to be TA with opposite sign. But if I start from the right side, then this 4,000, it will be on the shaft B. For example, I like to draw the BC, free body of BC. So this is point C, this is point B. What is the torque at point C? There is a torque at point C, anti-clockwise, right? And value is TC. So how much will be torque at point B? Obviously opposite of this TC. So right
Opposite
over
of TC.
TC is anti-clockwise. So over here will be TC clockwise, right? I can say this one. Now I like to take the line AB. So if I'll take line AB, this is A, this is my point B. So at point A, you cannot change it because at point A, already you have a anti-clockwise reaction TA, right? Now you have to say how much will be reaction at point B. So at point B, there is a reaction force 4,000. You cannot put it over here, then it will be unbalanced because both N has to be same. So this is balance. So this 4,000, now you need to put right over here. This 4,000. Now, if you look, if you like to join to shaft AB and BC join together, then you see this TC is coming extra force, right? This TC originally is not there. So you need to take out the TC. How we can take out? Right over here, TC is clockwise. So at point B, you can put TC anti-clockwise. This anti-clockwise. Then you join together, then what will happen? This TC clockwise and this TC anti-clockwise, both will be cancelled out. So you will have TA 4,000, then you have only TC. So this one now, line AB, you can represent with single, instead of two arrow, you can represent with single arrow. How? This TC, if I make clockwise, then it will be minus TC. So if I like to make a just one line, then I can see over here 4,000 minus TC. So this is balance. Okay. In that case, TA will be how much? In that case, TA will be equal to 4,000 minus TC. Okay. 4,000 minus TC. So any way you can solve it. You just need to make sure that your free body diagram is balanced. I think you already did this kind of job, right? Problem. Like you have a bar, and this bar, you have a one force over here. Other force might be coming at this point, might be other force over here. Then one force over here, other force going over here. Right? What you did to solve this type of problem, axial problem? You cut the body and make the individual free body, then figure out the load, right? So same way I did this one. It's very simple. Okay. So this chapter is finished. Before this chapter finish, I like to mention you something. You should give attention that might come in the exam. Sometime I say something I normally don't put in your lecture sheet, and sometimes I don't write in the board. I just talk. I like that the students should write down some important point. Okay, and sometimes you will see that that kind of problem or short question already came in the exam. So what I like to say, this one, you have only one shaft, right, at the one point, and only one torque, TC. But sometimes you might have a shaft, say this shaft, then attached to it, I took circle out, I took this one. Say this other shaft joined together, there's a one more shaft joined together. And now you have a torque right over here, 400. This is clockwise, right? Then you have a torque right over here, anti-clockwise 100. Right over here, you have clockwise, say 600. So 6, and right over here, clockwise, you have 300. So 400, 100, 600, 300. Now, if I say this is shaft A, this is B, this is C, this is D. And say length is given in the problem. Diameter, everything is known. If I say figure out the maximum shear stress in the shaft, or figure out the shear stress in its shaft, how we can solve it? You might say, okay, shaft BC torque is 600, and CD torque is also 600, and A is 400, AB is 400. You can say, but before do that, you have to make the free body of the diagram. Okay, so you will see this is 300. If you take summation of torque, this is, say clockwise is positive, then this 400 positive. Anti-clockwise 100 is negative. 600 also anti-clockwise, so 00. But this 300 clockwise, so positive. Now what do you see? Summation of torque equal to 0. That means this shaft is balanced. Now, if I say need to figure out the shear stress in each shaft, then you need the how much shaft torque is working at section 1. That's why I'm saying how much torque is at T1, how much torque is working at section 2, how much torque is working at section 3. Then you can figure out the shear stress. Now, how will you be able to figure out the shear stress in that case? Torque, how we can figure out? You have two options. You can draw a free body, FBD, or other one, you can figure out a torque diagram. You draw shear diagram, then there is one more diagram, is called torque diagram. So if you draw the torque diagram, then you will know how much the shear torque working in each section. So you see, you got bending moment diagram, you got shear diagram. Now we are getting one more diagram that is called torque diagram. So torque diagram, how it is work. Let me erase those things. Then I can draw a torque diagram and explain it. Torque diagram is same as bending, like kind of shear diagram. For example, along the length of the shaft, I am taking horizontal axis. This is length of the shaft, and vertical direction is the torque. Now you have to think that which way is positive, which way negative. So this is my point A, So this is say point B, this is C, this is point D, just for example. So this is D, this is C, this is B, A, B, C, D. Now, I like to make a torque diagram. How we can do? In the vertical axis, I will set torque. And which one you take positive? Any direction you can take positive. So I am thinking clockwise is positive. That means clockwise is positive, I am thinking. So at point A, how much the torque? 400, it's clockwise, right? So this is positive. So say this mass is 400. Then you draw a line until point B, because until point B, there's nothing changing. So clockwise positive over here, 400. At point B, you have minus anti-clockwise 100. So at point B, your torque will be how much? 400 minus 100, right? That means positive 3. So you come right over here, minus, right over here, 300. You write down over here. So this is 400, and you know this one is 300. So it remained constant until it came at point B. Okay. So at point B, no, we already came in point B. Point B, right over here, we are getting 300 because 400 minus this 100. So right over here, 300 until point C, it remained constant. So come to point C. I have to make a straight line. So let's say point C coming over here. So this is your 300 line. At point C, I came in, I see there is 600 anti-clockwise. So this is positive. So you have positive 300 clockwise minus 600 anti-clockwise. So what do you have? You have 300 minus. So then you come down bottom, 300 minus. So go gradually to the right side, remain constant. You came in over here. At point D, you have 300 clockwise. So this is positive 300, this is negative 300. So ultimately it comes 0. So right over here, you got 300. Over here, 300. Over here, 400. That means maximum torque in this problem is shaft AB. So this is one option. By drawing shear diagram, you can say which shaft is carrying higher load or which shaft is critical. Other thing you can do that you draw the free body diagram of each shaft. So how you will draw the free body diagram of each shaft? You see, 1 second. At first, you take AB. So I don't have space over here. Okay, I'm just drawing right over here. So I am taking shaft AB. You start from the left side. You can start from any side, but I start with the left side. So this 400 at point A, you cannot change. So this is clockwise 400. So how much will be at point B then? This is letter A, this is B. How much will be point B? This is clockwise. So at point B, there will be anti-clockwise 400. Now we see line AB is balanced. Now you take the line BC, then you solve it. You take line BC, how we can take it? You see again that one at point B, we have only 100, but there is no 400 load at point B, right? But you over here, you put 400. So you need to take out this 400. How we can take out? I'm drawing line for shaft BC. This is my B, this is my point C. So at point B, you see only 100 anti-clockwise, but I don't see anything anti-clockwise 400 over here in the main problem. So take it out first 400. This is anti-clockwise. So over here you put a clockwise 400. So if you close together, then what will happen? This 400 and this 400 will be cancel out. Now, let me write down clearly a little bit, then it will be clear. So we are getting right over here 400. But at point B, there is a 300 anti-clockwise. So this is clockwise and 300 anti-clockwise. I'm sorry, it's 100. So 400 minus 100, still 300 remain clockwise at point B. This is the resultant 300 clockwise. So over here, there will be anti-clockwise 300. Similarly, you draw the shaft CD and you check how much load there. And it has to be matched. If don't match, that means your result is wrong. Okay. So these two ways you can solve this type of problem. So if we got a time, then I can solve a couple of problems. Like you have a one shaft, you have a joint with another shaft, then one more shaft, and different point you have torque right over here, right over here, right over here. One go anti-clockwise, other one might be clockwise, might be this one, and might be right over here. You have a fixed support. So in that case, how we'll figure out the maximum torque in the shaft? So this kind of problem we'll solve it if we got the time. Okay. So this torsion chapter is finished. Okay. So any question? Anyone? Any question? No? No question?
No, sir.
Okay.
No, sir.
No question. Good. But we'll see something else right over here, that in column, I didn't solve one problem because normally I put that problem in as an assignment. That one kind of, it's saying you have two column, one is square and other one is circular cross section, and both have same length. That means L is same length of the shaft, material same. That means material property same. Then we'll say column N condition. N condition is same. So length same, material same, N condition same. So which column will carry more load? There is one more condition, that cross-sectional area is same. Then we need to know that how much load will be carried out. And we are saying the both column are long column. Both column is long column. If both column is long column, then which equation we will use? Anyone? Both one is long column. Tuhin, 123. You are there? Tuhin, 123. You are not here. Okay. Roll 35. Abu Bakar. You are front of the computer? Abu Bakar? No. Ifas. You are front of the computer? Ifas. Roll 50. 17 series. No. Roll 15, 17 series. Then roll 126. Abraham
Yes, sir.
Fahmi, you are here?
Yes, sir.
Okay. Tell me, if column is long column, then which equation we can use? Do you remember? We have
Sorry,
two
sir.
equations. if column is long column, then which equation you will use for figure out critical load of the column? Do you know
No, sir. Sorry.
how many equation we have column? Do you know?
Sir, two
Tell me.
equations.
Do you know the name?
No, sir.
No. Okay. Roll 144. Sabar. You there? Sabar is not there. Okay.
Yes, sir. I have a little bit network problem, sir.
Okay, you're there? Okay.
Yes, sir. I'm there.
Okay. Okay. Then tell me that how many equation we have in the column to figure out the critical load?
Sorry, sir. I don't know. I cannot participate this class fully because I have a network problem.
Okay. I understand that, but you have to go through the lecture sheet to understand. You know, if you don't understand, then you'll be behind. Our semester is almost going to finish. You know. Anyway, let's see. Asif, roll 121. You there, Asif? 121. You're not there. Okay. We have only three equations. One is for long column, Euler equation. Other one for short column, Johnson equation. And for eccentricity, we have second formula of column. So you see, so both column is a cross-section
Sir.
area is same.
Sir, roll 123 have message due
Okay.
in private.
Okay. I asked him question. Okay. So if area is same, then if you think that column with rectangular cross sections, each arm is R, A, and for circular radius is R, then what we can say? We can say A square, right? A square equal to pi into R square, because both areas same. So from here you get some relationship between, you can say A equal to some number, say some number into R, right? Or you can say R equal to A by some number. Now, by using the formula, you need to figure out PCR, P critical load. This equal to how much? Pi square E into C. What is the C? N condition. Divided by L by K square. So you use this equation. You first apply for square column, then use for circular column. Then figure out the P critical for circular column. Then you figure out P critical for square column. Then you can say, if I draw a test height over here, P critical for square column divided by P critical for circular column is ratio, you're getting 1.20. Then which column carrying more load? Anyone? No? Anyone? Anyone?
Sir, the circular one.
Circular one in the bottom. The ratio getting high, more than one.
So the square one.
Square one, right? If ratio is 1, then both will be the same. If bottom is heavier than the upper one, then ratio will be less than 1. So ratio you might get, based on the ratio, then you can say which column will carry more load. Okay. So this problem might be come in the exam, or I might put in a assignment. Okay. So this one was left from the column. Now we'll start a new chapter that is called pressure vessel. Okay. So before we start in the pressure vessel, you can take a short break. Okay. Come back at 2:08. Okay.
Okay,
Come
sir.
back at 2.